melt ice with that.
So what would happen if you lit it on fire?
Powder it or do whatever you did with the other sample.
Ooh, it smells so good.
Ryan.
Thank you.
Yeah. Okay, so here's what happens. When you put it in the fire, you excite the electrons in the outer shell of the copper, and they move to higher energy states. And then they want to get back down to their normal energy state, and to do that, they have to emit photons. And the photons that copper emits are green, and they're exactly a certain wavelength of green. And so we can detect copper by that green light that it gives off of exactly this wavelength.
Exactly one of those.
And if we see it burning in the sun, we can detect copper's wavelength and know copper is present. Okay? That's how you figure that out. But just like the electron in copper gets excited and comes back down, if you're in a burning core of the sun under super high heat and pressure, that electron gets excited, but it doesn't just go to a higher energy state, it just gets pulled off entirely. If you give an electron enough energy, it leaves its atom entirely. So that's kind of the basics there. So the core is 10 million Kelvin. 10 million Kelvin, that's really impressive.
Is that as bigger than the Earth still?
10% of the volume of the sun is still bigger than Earth.
Holy smokes, I thought it was tiny.
Right. It's tiny compared to the rest of the sun.
What did you say, 10 million what?
10 million Kelvin. So 27 million Fahrenheit. Hot, temperature-wise.
Kelvin? I've never
heard of Kelvin.
It means super duper 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 hot.
It's just like, you know how there's Celsius, there's Fahrenheit. Scientists use Kelvin because it can't be negative, and sometimes negative numbers are bad in math. If you've had enough math to know that you can't have a negative, or you can't have a zero in the denominator.
Right.
Well, if you get a temperature scale where there is no zero, then you never run into that problem. That's why they had to invent Kelvin.
Has no zero.
You never get to 0 Kelvin. At least they haven't. They've come really close. Deep space is like 0.2 Kelvin or something.
Like never zero.
They have
So
not.
there still is some. It's not like
They have not yet reached it. I would have said at one time they will never reach 0 Kelvin.
They'll find something.
I can't even say anything that way anymore. It's amazing what science has discovered and progressed, and so I don't know, but they haven't yet. So
What about the radiatives?
they've come very close. Well, hold on. We're still talking about the core because nuclear fusion. So, like I said, these baroprotons, they collide. They, if they get close enough to exchange a pion, they're stuck together. They become helium. Hooray! It's kind of complicated how that happens, but when it does happen, it's usually 4 hydrogens come together. Some of them have to be hydrogens that have a proton, a neutron, even though those are kind of rarer. And 4 hydrogens come together. They eventually make a helium and give off at least 1 neutron. Kind of confusing, but the helium gets pulled toward the core. So the inner core is more helium, the outer core is more hydrogen. This keeps going. When nuclear fusion happens, a tiny bit of mass is destroyed. Okay? The hydrogens that collide have more mass. What is going on over there? The hydrogens that collide have more mass than the helium does at the end. That tiny bit of mass that's destroyed, you guys have seen Einstein's equation. Right. Energy can be converted to mass. Mass can be converted to energy. And in this case, mass is being converted to energy. And you multiply by the speed of light squared, that's the constant of proportionality in that equation. So what that means is tiny bit of mass, right, times humongous number, right, 3 times 10 to the 8 meters per second squared, right, tiny bit of mass destroyed means huge amount of energy created. Okay? So when you look at those 2 nuclei, like say 2 hydrogens come together to form a helium, 0.7% of their mass is destroyed, and that creates this huge amount of energy, and more hydrogen in the sun is turning into helium. What is wrong?
Oh, nothing. I'm sorry. Something happened in English class.
Yay! I always worry that I have a kick me sign or something when people start to like laugh a little.
What happened?
No.
No.
Okay. So let's go back on track here. Right. All right. So this gives off a huge amount of energy. All right. You guys don't need to know that probably. All right. So we look at the spectrometer readings from outer space. We can see the wavelengths of light that are being put out. That's how we know the sun is mostly hydrogen and helium. That's how we can tell what other things there are in different distant objects. So the sun, somebody review here. The sun, what kind of nuclear reaction takes place in the sun, Max?
Nuclear fusion.
And Joshua?
So since the sun is converting from hydrogen to helium, does that mean the sun is losing?
Yes.
Yes.
So it's becoming lighter?
Right. So
But for only like a second.
Mass isn't weight.
Never mind.
it isn't when it's under the influence of gravity. So yeah.
Yeah.
So the gravitational pull comes into it every second.
But,
No,
yeah.
but then it blows up again. Isn't that the thing? Fly and then...
But it's
Oh, never mind.
continuously destroying mass. Right. So then
That would be
what's the
nuclear
next
fission,
zone
right?
of the sun?
If it destroys mass, that'd be nuclear fission, right? Or no, it combines them to make less.
Radiative zone?
We'll get there.
Radioactive.
The
Radiated.
I've never heard another person say this radiative zone.
Radiative zone.
So essentially, when nuclear fusion occurs in the sun and its energy is produced, it travels out, and just like a radiator emits heat, right? It travels, and it travels somewhat slowly, actually, because the photons of energy, right, light photons, kind of don't travel a straight path. They bounce, they collide, they pass from one thing to another. Just like we talked about when they pass through glass, right? This photon that enters here isn't the photon that comes out here. It energizes one particle, energizes, and passes that way. So it's kind of a more slow passage than through deep space as it travels through this. This is the biggest region of the sun, and all you really need to know about it is that the electromagnetic radiation, all of those wavelengths that are produced, visible light, all the other types of light, pass through and get out. And then we have the next zone, which is what?
Convection zone.
The convection zone. So you guys have seen something similar to this in the atmosphere, right? Where, of course, since this is near the core, it's very hot. So things here in the inner part of the convection zone are hot. They rise up. They transfer some of their heat out. They that are cooler, so they sink back down because you know that cooler things are denser than hotter things. So you get this convection current set up in the convection zone. It's just a loop, and it, all through here, right? You guys are goofy today. Dude. Here. So as long as there's no kick me sign on me, we're all right.
Open a window.
So then we get to the part of the sun that we can see here at the surface. I should probably have done that in a different color. And that's called the photosphere. We can see it. The photosphere is the first layer of the sun's atmosphere. It is the part that you see. It's the coolest part of the sun at 6,000 degrees Kelvin.
The coolest part of the
Really
sun.
hot. It's hot. And there are sunspots, which are, a comfortable 4,500 degree Kelvin. So sunspots, 4,500 degrees.
That's totally
Kelvin.
comfortable.
No worries about those
Or like a
sunspots.
dragon.
Right. So this, it comes.
That the very outer You talking about the photosphere? That's 4,500.
The photosphere is 6,000 Kelvin. The sunspots are cooler by a little bit, sometimes 4,500.
How much is the radiation?
Well, this is the photosphere. So here's the fun part. Calm down, take a deep breath, hold it. There you go.
6,000.
So the photosphere, the principle here is that's the layer of the sun that we can see, because gases are more transparent the hotter they are. The cooler part of the sun is the part that you can see because it's less transparent than all the hotter parts. Okay? So the sunspots are especially visible because they're even cooler. The photosphere is visible to us because it's the coolest overall surface area of the sun. But there are layers outside the photosphere that are strangely hotter. So other layers of the sun's atmosphere, which I don't think you have to actually know about, the chromosphere and the corona. So there are other layers. They actually get hotter, which is weird.
Is that where the solar flare, not solar flare, it's just like the stuff happens, like where it just goes like out and then.
The solar flares, they reach pretty high. The chromosphere and the corona are only visible during a solar eclipse when the other parts of the sun are blocked.
That's why it has the little like.
Right. They're actually hotter than the photosphere, which is what we can see. That's really complicated, and I think maybe I won't explain to you why that is. Sunspots are caused by the sun's magnetic field, which we've talked about, which recently, I think, flipped finally.
Really?
Yeah, so it's a really interesting thing to... Like the sun had a North Pole and a South Pole, and now it has a South Pole and a North
How does it
Pole.
do that?
The Earth does that too. And
We don't know why, right? We're not sure.
well, there are theories, but we don't know which of them is the most well, we know which is the most likely. Oh my goodness, leave the window open, it's fine. I need this.
Actually, don't leave the window open.
Is it hot out? It's hot.
They're letting in
Close
bugs.
it if it's really
bugs
hot.
letting in
Oh,
bugs and
close it
pollen.
if there's bugs. I don't want any bugs. Oh my goodness, you guys. Focus.
Study guide.
The chromosphere.
Corona.
CH.
The
And
chromosphere is a CH,
Okay.
and the corona is CORONA. And I don't think the book even talks about either.
I'm just writing it down.
Let me write down, what does the K stand for?
Kelvin.
Kelvin.
Kelvin. Kelvin.
Sounds for kids.
There's only one pen that actually works here. Kelvin is a temperature scale, just like Celsius or Fahrenheit. I'll teach you guys in chemistry because you have to use it when you're dealing with gases, because gases can't have a zero in the denominator of their equations.
How'd you spell the other one? Coronasphere?
Corona, it's just corona.
Oh,
So chromosphere.
Thank you. I
And
just
then outside of that is the corona. And those are part of the sun's
like
atmosphere.
corona light.
They get actually hotter than the photosphere. They get hotter as you move away from the sun, which is completely crazy. And so we've talked about fusion, right? Two nuclei that are small coming together and forming one larger nucleus, nuclear fusion. So when we use nuclear energy here on Earth in a nuclear reactor, are we doing fusion like the sun does?
No, we're using fission. It's nuclear fission.
Right.
Because we can't do nuclear fusion because we'd have to recreate our Earth.
We
Because of
actually
the amount
can.
we can, but I thought
Yes.
the amount of pressure we have in the core compared to the amount of pressure we have on Earth, like you can't replicate that.
So here's the deal.
You don't
The
have the
sun does
technology to do
fusion. It takes two hydrogen and makes a helium. There are other kinds of fusion that make heavier and heavier elements. You can use fusion to make heavier and heavier elements right up to uranium, and then you can't.
So you can do nuclear fusion here?
Yes. And
He said it was impossible. Not saying that everything he says goes, but
he said fusion.
no fusion. He said
He said we don't have the technology
we don't
to
have the
do it
technology.
yet.
It's possible, but the way we'd have to recreate our Earth to build a.
People do fusion all the time on Earth, actually.
Really?
And what you do is you get some strong magnets, you suspend a ball of plasma in the center of the magnetic field,
Oh, that sounds cool.
because there's no
actually.
container that can hold it. It's like a little sun. In fact, I watched a video. Actually, the boy's name is Taylor Wilson. If you want to watch an interesting TED Talk or YouTube video, Taylor Wilson is like 19 now. When he was 14, he achieved nuclear fission in his garage. Don't try this at home. Yeah.
Nuclear
Was there a
fusion in his
visit? Can you
garage.
send us a
Wait,
link
I'm so
to the
confused.
video?
Like in the book, it says you can't do that here.
Yeah.
So it's totally
Yeah.
possible.
No, I think what he's saying is we can't use fusion like
To make
the sun
electricity.
does.
That's what it was,
And we
to make
can.
electricity. Oh.
It just takes more energy to do it than it produces.
He just says we haven't mastered the process yet.
Yes. So we can do
Doesn't sound very
fusion.
efficient at
It
all.
Right. You actually spend energy to get it. Like that would be like investing in the stock market where you give them $200 and you get $100 back. That's
Lost time.
exactly what fusion is for us now. We can put in
Oh,
a
I
ton of
see.
energy, do fusion as a fun parlor trick, but what we get out is much less energy than we put in. So we're not
trying to
making
figure out a way to change that.
Like
right.
going to
And
casino.
this boy Taylor Wilson is working on the problem. And he's unbelievable. You really should.
I'm looking him up.
So
Look
where,
his stuff
it says that 80% of the country runs on electricity produced by nuclear power plants,
No.
which
No,
Oh, in
that's
France, okay. I'm like, not America, I'm pretty sure. I think we're about 20% U.S. electricity, about 20% of the U.S. is nuclear produced. But other than hydroelectric, all power plants are essentially the same. You heat up water, whether it's using the heat from a nuclear reaction, fission, or by burning coal, wood, gas, whatever you're burning. You heat up water that produces steam. That steam rises and turns the turbine, and that's what produces the electricity. So we only use nuclear fuel in a reactor to heat water. That's its whole goal, just like a coal-burning power plant would. It just doesn't produce the carbon dioxide and the sulfur pollutants that cause acid rain and global warming.
because no one
Not
wants
to
that.
go to another hot button topic, but just saying, nuclear power doesn't do that. It just produces nuclear waste that lasts pretty much forever, thousands of years.
Yeah, no biggie.
And our boy Taylor Wilson has worked on that problem too. So you guys might not inherit the nuclear waste of my grandparents.
That's cool.
Yes.
Yeah.
He's only 19.
Oh wow.
That's brilliant.
I know.
Here's the next
Probably
one.
graduated college at like 15.
Yeah, I'm pretty sure he doesn't need to go to college at all.
He probably has already gotten a job and doesn't even need like
He didn't want the government to hire him just because then he would
Well, he just works in his garage?
and stuff. No, he actually. Well, just watch the videos. It's amazing.
this would be like
But
he
that's
didn't
what
really
we
want
want
to
the
discover
government.
more if that's your
So,
job, I guess. Does that make sense?
Fusion on Earth is possible. You just have to suspend the little ball of plasma in a magnetic field that's super strong, so it can like be a little burning ball of stuff
Oh,
and
is that
harness
all?
the power, which we can't really do efficiently. So we don't get as much power in as we or out as we put into it. So it's bad. But fusion, like what the sun does, doesn't produce that awful nuclear waste that fission does. So it doesn't have that waste that lasts forever. If we could do it, it would be a really great way to produce power. So far, I haven't figured that out yet. So, nuclear fission is the way that we can produce power. Nuclear fission is kind of the opposite of fusion. You take a big nucleus of a certain isotope, right? So you know that uranium, for example, has multiple isotopes. Uranium-235 is the common isotope. No, 238 is the common isotope. So uranium-238 is common. Uranium-235 is about 1 out of every 140 uranium atoms. So one of them out of every 140 atoms is 235. And that's the isotope that we need to use to do nuclear fission. But that is not concentrated enough in a sample of uranium to actually get the reaction going. So let's kind of talk about that here. Where to go here? Where do we go with this? So the big breakthrough in the 30s. My history is really bad.
What are you trying to
Of getting nuclear fission to work on a large scale. 30s, 40s Manhattan Project.
I'm gonna say after World War
War II.
after World War II, so around.
No, because
50.
we ended World War II with a nuclear weapon. Yeah.
Hiroshima.
Yeah, but we made the bomb before we made the. I mean,
Yes, we didn't use it, but they had to know how to.
oh, you're saying when it came around?
Yes, 30s.
Like, okay, so
Was it
that's
the
definitely during World War II.
30s, 40s, late 30s, early 40s.
It's gonna be mid 40s.
Okay. So, our history might be rough, but they figured out the secret of separating these isotopes. Now, you guys learned earlier in the year that isotopes are chemically identical in their properties, right? Except that this one has 3 more neutrons than this one. Neutrons don't really affect chemical properties. It's only a difference in the mass of the nucleus, and it's tiny. So separating them is done with a centrifuge. You spin it. The heavier things travel further down to the bottom of the thing that you're centrifuging. Lighter things stay up here. I have no idea beyond that because it's pretty heavily guarded secret how to separate isotopes of uranium. But that's the general idea, is somehow they're able to centrifuge it to separate the differences in mass, to concentrate the amount of U-235, and then purify it so there's more and more and more U-235 in a sample. So instead of 1 out of every 140, there'd be more than 1, lots and lots out of every 140, for example. So then, once you have enough, you call that critical mass. Critical mass is the amount needed to sustain a chain reaction. And here's how that works. Chain reaction. I'll even spell it out. I never spell the word reaction ever all the way out. But, so you get a chain reaction. So here's kind of the deal. When you have a neutron and a U-235, and you get that neutron moving at a super high speed, and it hits the U-235, it can split it into 2 parts. It has to hit just right. All kinds of little technicalities there. And it will split into what? These are not things I memorize at all. Not that. Where are we? Here we are. It'll split into a barium and a krypton and 3 neutrons. Now, if you have, okay, here's the deal. If you peel a big potato and then you peel the same mass in small potatoes, which pile of peelings will be bigger?
The small potato.
I see somebody helps Mom. That's good. So why?
Because the small potatoes combined have more surface area.
Exactly. Okay, so think if you have a little ball like this, the surface area compared to the whole volume is bigger than something like this surface area to volume, right? The proportion. So when you get this to happen and you have enough of the uranium and the concentration of 235, the one that'll do fission, is enough in that, then these 3 neutrons are able to hit 2, maybe 3 other atoms, split them, giving off 3 more. Then you get an exponential growth. If the surface area isn't big enough, they eventually get out of the sample and the chain reaction doesn't happen.